Hello, I think my I hope my audio is audible. My voice is audible. Yeah. So so on October 16th, I took a session on 1 hour extra session on the topic of machine learning. But unfortunately, I couldn't record it. Okay. So so I was asked to record the session again because there's the only way we can show that we have done the session. So as you can see, the um notebook was created on 16th of October on 2024 at 5 p.m. and I taught all those things in the lecture, and those who have attended would have uh, known all these things. Okay, but since I am recording again, I will be showing these notes and I'll be explaining what I taught in that session. So if you're watching it as a recorded session, you can um, yeah, if you're watching it as a recorded session, you can follow along and be with me. So I'll give you some time to look at these questions and answers. Okay, and I'll explain it in a minute. And since I'll not be writing a lot of things now, it will take a very short amount of time to record this, but I'll be taking breaks in between to for you to read this and solve these things before I explain them, because it will be very little time for me to explain. Like it will take very little time for me to explain all these things, right? Okay. Sorry, I was not recording it again, so I forgot it. So I'll start again. In week 2, we are currently looking at this problem where we have a neural network function f of x that is equals to ax plus b, where x is the input, fx is the output. We can rename fx as y, and the set of parameters are a and b. Okay. And as per the task, what we need to do is that we need to find the set of best parameters which best describes this data or best describe this x and y pair, right? So let's say the x and y pair are the following: x equals to -1, y equals to, when x equals to -1, y equals to 0.0319, when x equals to 0, y equals to 0.8692, when x equals to 1, y equals to 1.9566, when x equals to 2, y equals to 3.0343. Okay. So given this set of x and y pairs, we need to find the best value of a and b. So the procedure to do this is that we will first try with, first go along all the options that we have in our question. Like option A is 1 and 1, option B is 1 and 2, option C is 2 and 1, option D is 2 and 2. So after going through all these options or one after another, what we will do is that we will find the value of y for all these corresponding options. And once we get the values for all these corresponding options, we'll pick the options with the lowest value, right? So as you can see, what I've done is that I have calculated the value of y for the given value of x for the set of parameters 1 and 1. You can see here in the first and the option A, the value comes out to be 0.0319, 0.8692, 1.9566, 3.0343, right? And we have a set of y for it as well. So if you see, okay, sorry. So we have the set of y here, and we have the value that we have calculated is here. So the value that we are calculating is ax plus b, right? So that is 1 into -1 plus 1. Here it will be 0, here it will be 1, 2, and 3. So these are the predicted value of y, and these are the actual value of y that we have with us. What I need to do is that I need to find the difference between them. And for simplicity, let's just take all the values up to 1 decimal place and calculate the difference. And we took them and we calculated the difference. The difference came the difference come out to be 0, 0.1, 0.1, and and we sum it, and the sum of all these values comes out to be 0.2, right? So what we can do is that we can note this 0.2 value. Similarly, if we go to option B, as you can see, the value of the value of a and b is same, and we are sorry, the value of x is same. We're changing the value of a and b. Given that we have the same value of x, increasing the value of a and b will always increase the value of y, and the difference will be much more as well, right? So similarly, when we try with 1 and 2, the value increased. So the value come out to be, so earlier it was 0, 1, 2, 3. Now it is 1, 2, 3, 4. Okay. So similarly, the difference also increased, and it is like 1, 1.1, 1.0, and 1.0. And the sums out to be 4.1. Similarly, if we try to find for 2 and 1, it will happen. And for 2 and 2, it will similarly happen. So by evaluating all these things, we came to an conclusion that the value of parameter, if it is 1 and 1, it is giving us the lowest error. Hence, it is the optimal parameter that describes the data. Then option 1 is correct, right? Okay. We'll go to the second question that is picked from week 5. Okay. So uh, we are saying, let's say there is a 3-layer neural network, 10 input layer. There are 10 neuron in the input layer, and there are 5 hidden units, and there are 10 output units. So how many parameters are there? So how many trainable parameters are there? Assume that each layer has a set of weights, and each layer has a set of biases. Okay. So calculate it. I'll give some time if you're seeing the recorded version, like 5 minutes, and I'll describe it after that. Okay, so it's a very simple question actually. Um, so what you do is that we draw this, like there's 10 input layer and there is 5 hidden layer and 10 output layer. So the weight matrix, so as you can see here, there will be weight matrix between this layer and there's a weight matrix between these two layers. So the matrix size would be 10 cross 5 because the input is 10 and output is 5. Here the matrix size will be 5 cross 10. There will be input is 5 and output is 10. So this is 10 times 5 is 50 and 5 times 10 is 50. So we have 50 plus 50, that is 100 parameters or 100 weights. And we also need to add biases as well. So here the 5 units will require 5 biases, and here the 10 units will require 10 biases, and the 10 input units doesn't require any biases. So here it sums up to be 55, and here's it sums up to be 60. So if we add them together, it is 55 plus 60 equals to 115. So the total number of trainable parameters is 115. Okay. So this is the solution to the question. We discussed another question as well, another two questions as well. So there is a question that says that let's say this is a data set of x1, x2, and y. When x1, x2 is -1 and -1, the value of y is -1. When x1, x2 is 1 and -1, the value is 1. When it is -1 and 1, the value is 1. When the value is 1 and 1, it is -1. So it is a type of you can say like it's a XOR operation. And what you need to what we are trying to say that the XOR operation here is so the XOR operation here is the XOR operation here is not linearly separable. Okay, so one of the way by which we make a data set which is not linearly separable to separable is by doing a transformation on x1, x2 so that it will be linearly separable. So it is saying there are three options. One is rotating x1 and x2 by a fixed angle. Second is adding a dimension z that equals x times y. And the third is adding a dimension of z that is x square plus y square. But here, as I say, the z equals x times y is not actually x and y, it's actually x1 and y1. So in option 3 also z equals x square and y square and not x square and x1 square and x2 square and not x square plus y square. Okay, so try to solve this one as well. I'll come back again in a few minutes. Okay, so explaining this question, I'm gonna explain this question. That is, let's say you have this XOR function, right? XOR function is not actually linearly separable. But what we can do is that, so let's say like, rotating x1 and x2 by a fixed angle. Rotating x1 and x2 by a fixed angle will not change anything because it will be moving on the same plane. As you can see, as I have noted here, it is moving on the same plane and we're moving everything 90-degree, right? So that's not gonna work. Okay. And the second option was to transform it to a different dimension g that equals x1 times x2. Okay. So if I write down the z here, it will be -1 -1 1 1 -1 -1 -1 1 -1 1 1 1, and the corresponding y would be -1 1 1 -1. Okay. So if you look at it, so I have plotted it here actually, to be honest. So I plotted it here. So you just have to uh, you know you just have to see how all these things are panning out. So you plotted everything. So as you can see now, the all these point -1 -1 1. So we need to differentiate between this first and last line from second and third line, right? So the first and last line is marked with blue, and the second and third line is marked with pink. You can see this point is, let's say, 1 1 1, and this is -1 -1 1. This is -1 1 plus -1, and this 1 -1 -1. You can see now in 3D space, those 3 points are completely um, distinctly different. So you can put a plane in between them. Okay. So this makes this representation linearly separable. So hence option 2 is correct. Okay. So moving on to the next question. Let's say there is this confusion matrix. Okay. So I'm not gonna show you the answer first. Let's say there is this confusion matrix, and there is this actual positive and predicted positive. There is this actual negative and predicted negative. And so all these values are there. So for the simplicity, I have written all these things. This is called true positive, this is called true negative, this is called false positive, and this is called false negative. And this is the precision, recall, and accuracy. So you need to calculate this precision, recall, and accuracy. So I think I'm going to record for next 10 minutes again. So I'll take a pause for 5-10 minutes, and then I'll directly discuss these terms and what they mean, and how to calculate them, and the formula for this. Okay. Okay, so this is the last question I'm going to discuss. So this is very simple. So we have the true positive. So if the actually the data is positive and we predicted it as positive, it is called true positive. If it is actually positive but predicted as negative, it's called false negative, because it is not negative, it is falsely classified as, or yeah, classified as negative. Then we have false positive, which is actual negative but classified as positive. We have false true negative, that is actual negative and we classified it as negative. So we have this first term is called precision. So precision is how precisely we did the prediction, we did the did our thing. So how precisely, so to measure the preciseness of a prediction, what you do is that we take the thing, we take the value that is actually we predicted positive, that is true positive, uh, among the all the true positive and false positive. That is how precise our prediction is. So if you see precision is true positive by false positive, then there is recall. Recall is how much we predicted right out of um, uh, all the positive values, that is true positive plus false negative. So the recall value would be true positive by true positive plus false negative. And the last one is accuracy. Accuracy is how much of the data is actually classified correctly out of all the data. So that is true positive plus false positive, true positive plus true negative by everything else. Okay. So if you calculate the precision, it will be 85 by 85 plus 20. If you calculate the recall, it is 85 by 85 plus 15, and both comes out to be 0.81 and 0.85. And accuracy is true positive plus true negative by true positive plus false positive plus true negative plus false negative. That is 85 plus 80 by 85 plus 15 plus 20 plus 80. That is 165 by 200. That is equal to 82.5 by 100, which is equal to 0.825, or you can say 0.83. I think I'll stop the recording for today now, so you can watch this video. This video is like I took a question, then I took a pause. This is because like I have already did that taught this already, and I forgot to record that, so I had to stretch it down to 45 seconds or 45 minutes, right? And upload the video. So if you make sure to skip it, and all the best for your, if you're watching this, all the best for your exams, and I'll see you in the next semester. Thank you.